Hello everybody. This presentation will cover the topics of chemical equilibrium and the rates of chemical reactions. Let's take a look at our learning objectives for this unit. Goal 1 says the student will demonstrate the ability to describe factors which are going to affect the rate of chemical reactions. Goal 2 says students will demonstrate the ability to describe energy changes that occur during a chemical reaction or a chemical process. Finally, Goal 3 states that students will demonstrate the ability to explain chemical equilibrium. Let's take a look at some key vocabulary we'll use during this unit. Collision theory. This states that reactants must collide with each other. That means they have to bump into each other with enough energy to cause the conversion which will form chemical products. The rate at which this occurs is going to depend on a number of factors, including temperature, concentration of reactants, and the actual nature of the reactants themselves. Now, an effective collision relates to this concept. This is a collision between two reactants which is actually going to trigger a chemical change. Please note that not all collisions are effective collisions. Sometimes reactants may bump into each other and then they will travel away and do their own things and no chemical reaction will occur. Reaction rate, this is where we're looking at how fast effective collisions are going to be occurring, which is going to allow for the conversion of reactants to form products. Activation energy is the minimum energy which is required to have an effective collision which will allow the conversion of reactants to products. Exothermic reactions are ones which will involve the release of heat energy. The enthalpy change here will be negative. Delta H means enthalpy. This is the heat of reaction. We'll take a closer look at this with a future slide. Finally, we have endothermic reactions. These are reactions in which heat is going to be absorbed. The enthalpy change here will be positive. An example of an exothermic reaction would be if we are burning something. An example of an endothermic process would be the instant ice packs that when you shake them up and cause the reaction to occur, they actually absorb heat energy so that if you put that on your shoulder, it will feel cold because it's pulling heat energy out of your body. Let's look at some factors that will change the rates of chemical reactions. First, an increase in temperature will make the reaction rate increase because we know that higher temperatures mean faster moving particles. Faster moving particles mean more collisions, plus the collisions are more energetic. A catalyst is a chemical substance which will make a reaction rate increase. Decrease in particle size will cause the reaction rate to increase because of increased surface area. Finally, an increase in concentration of reactants will make the reaction rate go up. Let's take a look at how we would use the terminology enthalpy and enthalpy change to describe endothermic and exothermic processes. First of all, enthalpy, this means the heat of a reaction. Now, technically, enthalpy is equal to the internal energy of a system plus the pressure multiplied by the volume. For our purposes, though, we can simplify, where the enthalpy will be equal to the heat of the products, or the enthalpy of the products, minus the heat or the enthalpy of the reactants, where again, HP is the heat energy content of products in a chemical process, HR would be the heat energy content of reactants in that process. Here's a look at a potential energy diagram for an exothermic process. If we were going to use some terminology we were just looking at, the heat of the reactants, the enthalpy of the reactants would be located right here on the potential energy scale. The enthalpy of the products would be located here. So by subtracting we find the difference, which is the delta H, that is the enthalpy of the reaction. Here's the reaction pathway. We can think of this as time elapsed. So the beginning of the reaction, end of the reaction. This energy right here, E sub A, refers to the energy of activation. This is the startup energy required to trigger the start of a chemical change process. Here we see comparisons of two different times where we're running an exothermic process. One where we are not using a catalyst, a second time when we are using a catalyst. Now we can see that the enthalpy change for this reaction would actually not be changed by the use of a catalyst. What is going to be decreased, however, is the activation energy or the startup energy. And this is the main reason why catalysts will make chemical reactions proceed more quickly. It's important at this time that we differentiate between heat and temperature. Temperature is a term which refers to the average kinetic energy of particles of a substance. Please remember that kinetic energy refers to the energy of movement. We can calculate energy using the equation KE equals 1/2 mv squared, where m is the mass and v is the velocity. Heat is a slightly different term. This refers to energy which will be transferred between two objects that have a difference in temperature. In an upcoming lab, we will be using the technique called calorimetry to determine the caloric content of a number of different food samples. In order to do this, we will be finding the enthalpy or the heat change for the foods. This is sometimes called Q. We'll calculate that using this equation, mc delta T. Again, Q stands for energy, which we'll measure in calories. M is for the mass of water in a soda can. C is specific heat capacity. We will use the value 1 calorie per gram degree Celsius. Sometimes you'll run into this value, 4.186 joules per gram degree Celsius. And delta T will be the change in the water temperature. So by measuring how much energy content is transferred to the water in the can, we can therefore determine the amount of energy which was released when we burn the food samples we are testing. Here is an example of a reversible reaction process. Please note the arrow here indicates that the reaction can proceed either to the right, forming ammonia and giving off heat, or it can proceed to the left, which would generate nitrogen gas and hydrogen gas. So depending on the conditions that we put these reactants and products in, we can either shift the equilibrium, the balancing point, to the left or to the right. There are certain things we can do to cause for the formation of more ammonia. There are other changes we could make to a reaction system which would cause us to decrease the amount of ammonia and generate more nitrogen and more hydrogen. An important concept in chemistry is dynamic equilibrium, which states that forward and reverse reactions are balanced so that the amount of products and reactants is not going to change. I'd like to remind all of my students to reference back to the dynamic equilibrium we discussed when we were talking about the dissolving of sodium chloride in water. Now again, as we consider dynamic equilibrium, we need to understand that the rate of reactants to form products, that would be the forward reaction producing ammonia, is going to be equal to the rate of the reverse process when ammonia breaks apart to form nitrogen and hydrogen. Because the forward and reverse processes are balanced, the overall amounts of reactants and products is not going to change, even though individual atoms of nitrogen and hydrogen may transition back and forth in going from ammonia to being the separate elements. Please note that the level of reactants does not necessarily need to be equal to the level of products. Let's take a look at an equilibrium expression. In order to solve equilibrium expressions, we will use the law of mass action, which can be summarized like this: products to the x over reactants to the y. There'll be an additional short YouTube video discussing this topic. Let's consider the reversible process of sulfur dioxide reacting with oxygen to form sulfur trioxide. The arrow here should go either direction. Products, my product is the sulfur trioxide. Because the coefficient is 2, I will square that amount. Because sulfur dioxide also has a coefficient 2 in front of it to write the balanced equation, we'll have for reactants SO2 squared, and this will be multiplied by the amount of O2. Please note that there is no exponent here because there is no coefficient that's used here. If we calculate a KEQ value, if we substitute in numerical values for the amounts of products and reactants, if we have a very large KEQ, this means that the formation of products is the favored process. If we have a very small KEQ, that means that reactants are favored. Le Chatelier's principle is applied to reversible processes to allow us to predict what changes will occur if we apply a stress to a reaction system. So here's the basic idea. If we apply a stress to a reaction system, the system is going to react in order to try to relieve this stress. Examples of stresses would include changing the amounts of either reactants or products, changing the temperature, or changing pressure. Now let's take a look at an example reaction. Again, the synthesis of ammonia, NH3. If we were to increase the amount of nitrogen, that is a reactant, the process is going to shift to favor the formation of ammonia because this will help to remove nitrogen which was added. Now, in B, if we increase the amount of ammonia, this is going to cause a shift to the left because the reverse process is going to break apart that ammonia into nitrogen, N2, and hydrogen, H2. if we were to decrease in C, if we were to decrease the amount of ammonia, so we're taking this away, the reaction equilibrium will now shift to favor the forward process, which will help to regenerate the ammonia that was being taken away. Let's look at an increase in temperature. Now we're going to shift to the left. Let's consider why this would be. The forward process is going to give off heat. So if we favor the forward process, we're actually going to increase temperature, which would add on to already increased temperature. However, if we do the reverse process, that's going to take away heat, which will help to cool in response to the stress. Finally, an increase in pressure is going to cause a shift to the right because we are going to decrease the number of gas particles. Here we have 4 moles of gas, here we only have 2. So by reducing the number of gas particles to 1/2, we can help to reduce the pressure. Let's consider reaction mechanisms. Now, I should start out by describing what an elementary reaction is. This is a chemical reaction process which would occur in a single step. Reaction mechanisms are ones where we're going to be describing chemical reactions which occur in 2 steps, 3 steps, 4 steps, so there are multiple steps in a chemical conversion process. So we have a series of steps that a reaction goes through to get from reactants to products. Intermediates are going to be substances which are formed temporarily. Catalysts are going to be involved in the reaction, but they will remain the same before and after, so they are unchanged by the overall process. Finally, the rate determining step is going to be the slowest step in the reaction mechanism. So let's consider the reaction of dinitrogen monoxide to form nitrogen and oxygen. So we can see here that in a slow step is going to be assisted by a platinum catalyst to break apart into nitrogen and a single oxygen atom. The formation of this single oxygen atom is difficult. That's why this step is going to take a long time. Now, once that occurs, the N2O can react with a second one, can react with that single oxygen formed here to produce N2 plus O2, and we're reforming that platinum catalyst. So the rate determining step would be this first one. The intermediates would be this one right here, the oxygen, single atom oxygen. The catalyst would be the platinum. To find the overall equation which describes this reaction, let's consider the 2 steps of the reaction mechanism. We can see that N2O shows up as a reactant in both processes, so we'll go ahead and add those to come up with 2 N2O. We see that the same thing will occur on the product side for N2, nitrogen. So once again, we will add those to come up with 2 N2. O2 shows up only one time as a product here, so we're going to write that down here. Also, we see that platinum shows up before and after in the same condition, so that's how we identify it as the catalyst for this process. Finally, because oxygen, the single atom, is formed here and then it's used up here, these oxygens will actually cancel each other out. So that's how we're identifying that as being an intermediate formed in this reaction mechanism. So the overall reaction here we would write as 2N2O yields 2N2 plus O2. And this is aided again by a platinum catalyst. We could write PT above the arrow to indicate its catalyst status. In our final slide, we will define entropy and free energy and then discuss their relationships to chemical reaction processes. So what is entropy? Entropy is the level of disorder in a system. A decrease in entropy, therefore, would mean that we're producing more order or more organization. Free energy is the amount of energy in a reaction that would be available to do work. Typically, we calculate Gibbs free energy, which is delta G. We don't actually do any Gibbs free energy problems in GT Chem. Finally, why are these things important for chemical reactions? We know that chemical reactions can be used to do work. For example, you drive your car, and this is powered by the burning of gasoline. Now, it's necessary to factor in both the entropy of a reaction and the energy levels of reactants and products to determine if reactions are going to be spontaneous or not, and to help us calculate how much energy they can help to produce. Please visit my YouTube channel for additional videos which will discuss the following topics in more detail. I'll take a look at equilibrium expressions, how to write them. We'll look at the effective concentration on reaction rates. We'll solve KEQ problems. We'll calculate enthalpy changes. We'll also take a look at specific heat calculations, specifically those used for calorimetry experiments.